Very good afternoon to you all. Good afternoon.
Good afternoon, teacher.
Okay, so today we have introduced latent heat. And before we have seen specific heat capacity, we have seen heat capacity. So now we want to introduce what we call latent heat. And by definition, latent heat is that amount of heat that you require to change the state of a substance at a constant temperature. In that case, we say the physical state of the substance has to change. So when you're defining, that is what we say is the amount of heat energy absorbed or given out when a substance is maintained at a constant temperature and has been made to change its physical state. So one can say latent heat is the amount of heat energy required or absorbed at a constant temperature and is used to change the physical state of a substance. So one should know that this occurs at a constant temperature. So there is no heat, there is no change in temperature when latent heat is being exhibited. Two, the physical state of the substance changes. For example, it can change from a gaseous state to a liquid state. It can change from a liquid state to a gaseous state. It can change from a physical solid state to a liquid state. And when it changes from a liquid to gas, we say it's evaporating. So evaporation takes place. And the latent heat we require there is called latent heat of vaporization. The same applies to when it is coming from a gas or from vapor back to a liquid. Still, you need latent heat of vaporization to bring it back to its other state of a liquid. Then if you are to change from a solid to a liquid, you require latent heat of fusion. That is from liquid to solid or solid to liquid. The reverse is true. You require the same amount of heat energy. Then for sublimation, that is moving from solid to gaseous state. That one we shall not discuss much about it right now, but still, it also should be occurring at a constant temperature if it is to occur anyway. And in that case, still the latent heat you require is that heat you require when there is no change in what? Temperature. So among the characteristics of this kind of heat, one is what I've mentioned. Characteristics of latent heat. One of them is that there is no change in temperature no change in temperature when a body absorbs latent heat. Then the second one causes the body to change state change state from one state to another, like I've mentioned. Whenever you have latent heat, there must be change of state. Okay? Latent heat cannot occur without a change in state. It also makes the internal potential energy of the substance to increase. The substance to increase. For example, how does that happen? When you look at solids and you bring that heat, it can break the intermolecular forces of attraction and bonds between the molecules. And by so doing, we shall have this crystalline structure of the solids changed from the structure it was before to a new structure. Perhaps it can be a liquid structure. For example, ice. You heat up ice, then it converts to water. The temperature at which ice converts to water is the same temperature at which water converts to ice. Okay? So it is from here that we can talk about the different types of latent heat. One, the latent heat of fusion. And I've mentioned this in my introduction as heat we require to change the state of a substance from a solid to liquid or liquid to solid. Okay, so in this sense, you will see that latent heat basically is the amount of heat energy one requires to convert a substance from solid to liquid state at a constant temperature. So you can say this is the amount of heat energy required to change a substance from liquid state or from solid to liquid state without change in temperature. And its SI units, the expression is H is equal to mLF. So latent heat of fusion is equal to heat out of the mass. So the SI unit of latent heat of fusion is actually joules per kilogram. Now, sometimes we shall also see what we call the specific latent heat of fusion. Yeah, whereby when it becomes specific, it is looking at a unit kg, a unit mass of a substance. So when we talk about specific latent heat, specific latent heat of fusion, you can say this is the amount of heat energy required to change the state of a unit mass of a kilogram or of 1 kilogram mass of a substance. The substance from solid to liquid. At a constant temperature. at a constant temperature. Then it is from here that we can also talk about also its SI units is just packages. Actually, this is the latent heat of fusion. This was just heat energy, which is latent heat. SI unit for latent heat. Because heat is energy, its SI unit is also joules. But when we come to latent heat of fusion, that one, the SI unit is joules per kilogram. It's not the same as latent heat. But if you say latent heat of fusion, there it's different from just latent heat. So we can also have the kinetic theory. The kinetic theory of fusion. How fusion exits, what happens when fusion is taking place. So I've already talked about a solid tending to go to a liquid. It goes there at a constant temperature, and I gave the closest example is ice. If ice is to melt, then it is melting at 0 degrees Celsius. When you measure the temperature of the ice, it should be to 0 degrees Celsius. The same applies when it is coming from the ice back to a liquid. Now, for a solid to melt, it means latent heat of fusion has to be supplied to that solid to melt. And in that case, the heat energy is required in breaking the strong intermolecular forces in the crystalline structure of the solid. That is, if I want this solid to melt and then become a liquid, the heat I'm going to apply is going to break the intermolecular forces that define the structure of, or that define the crystalline structure of the what? That define the crystalline structure of this solid substance that we are dealing with. So the molecules move. The molecules which are supposed to be in a position of fixed positions, they can now move closer and they can also move further apart. I.e., if they do that, their potential energy increases and also their kinetic energy. Their potential energy and kinetic energy remains a constant when they are doing that. But now, when they do that, because kinetic energy and potential energy have remained a constant, yeah, actually it's in this form. If you have the molecules, let me draw them here. If you have these molecules, which were initially in contact, not in contact, at fixed positions, because of the intermolecular forces of attraction. When the heat, which is latent heat, comes and it breaks away these molecules, I mean, these intermolecular forces of attraction, yeah, what is going to happen is their potential energy increases because of the positions changed. Whereas their kinetic energy remains constant. Now, since kinetic energy is directly proportional to temperature of the molecules, then the constant kinetic energy we have brings about a constant temperature. That is why latent heat of fusion occurs at a constant temperature. So we have seen that, one, for latent heat of fusion, two, being positioned to melt a solid to a liquid, we have to apply it to that solid. When it is applied to a solid, what happens? The energy is used in breaking the intermolecular crystalline structure of the solid. When the intermolecular crystalline structure of the solid has been broken, what is going to happen is the potential energy of the molecules is going to increase, whereas their kinetic energy is going to remain a constant. Now, when their kinetic energy has remained, because the kinetic energy is not supplied is not gained in a way that, because if kinetic energy was there, the molecules would move further apart. But what we do, we are just breaking the intermolecular forces of attraction. But the position of the molecules is what changes by increasing the potential energy. Then the kinetic energy, which they had before, is still the same. So because it has not changed, it is going to occur at a constant temperature. And thus, because K is directly proportional to temperature, the latent heat of fusion takes place at a constant temperature. So that is what the kinetic theory of fusion predicts. And I've submitted all that right up in your notes. You'll have to review and also visit the internet and read about them and see how best you can have all these interpretations handled. Then, determination of specific latent heat of fusion of ice. Whereby we can use one, the electrical method. The electrical method. And we are using this electrical method to determine or to predict the latent heat of fusion. Firstly, you need a rheostat. Connected to a battery, then to an ammeter. Okay, lose it, pull down. Sorry about this young physicist. Then, this electrical circuit is connected to a heater. And this heater, we can measure its voltage across it using a voltmeter. One of the errors here is people interchange, like I mentioned in the earlier experiments for electrical method, people interchange the ammeter to the position of the voltmeter and the voltmeter to the position of the ammeter. So if we are to have this as our ice, so if this is the ice, to take on such a shape, placed in a funnel. Then we can have our reservoir here to collect the water that has melted. So this is water collected. This is a filter funnel. This is lumps of dry ice. And this is our heater. And with this, we can see that the setup shows that the experiment is already working. And if the experiment is working, it shows that it is ready to be in action. Now, some people put there a switch. Some people can put here a switch. When they put the switch, they forget to mention that the switch is closed. So if you know you'll forget to mention the switch, please don't put it there. Straight away show that the experiment is already working. Otherwise, you lose the marks. So, dry ice or lumps of dry ice are placed in a funnel, and then the heating coil is placed in the ice. The heater is switched on and the stop clock is also started. The PDV across it is also measured, and the mass m of water collected in a time t seconds are recorded for the different various values of current I. The results are then tabulated, and if they are tabulated, we can include values like voltage, V. We can also include values like current I, amperes. We can also include mass in kgs. Then we can also get the rate of mass flow, mass per time. This is in kilograms per second. Then we can also get power, which is IV in watts. So that's the tabulation we can do, whereby we can consider electrical power supplied by the heater, first hold on, this internet wants to shut down. So I was saying electrical power supplied by the heater plus heat absorbed by the surrounding screen. So I was saying the electrical power supplied by the heater plus the heat absorbed by the surrounding is equal to the heat that has been absorbed by the ice per second. So electrical power supplied is IV plus the heat absorbed by the surrounding per second is equal to the latent heat of fusion absorbed by the ice, which is mass of the ice times the latent heat of fusion. Then from here, you can see that power can be made the subject as IV is equal to MLF minus H. Then you can plot a graph of power, IV. Against mass per second. Is plotted, and it's a linear graph. And if it's a linear graph, it doesn't pass through the origin because of some heat losses or some power loss due to the surrounding. And now, the intercept is the power due to the heat loss to the surrounding, and thus the slope is the latent heat of fusion. The slope of this graph. So with that, you can predict the latent heat of fusion of ice using the electrical method. No, I think I've interchanged the graph. It has to come and pass through down here. Let me make an adjustment here. If I sketch it like this, going down, when the power is 0, we shall have this as the initial mass, m naught. Then here we shall have h. So this is how the graph would look like. And this being the slope, S is equal to change in IV over change in mass, which is equal to latent heat of fusion. Where MO is the mass of ice, that would melt if the heater was off. So if there was no power, MO is the mass of ice initially. If the heater is off. H is the rate at which heat is absorbed from the surrounding. So that is method 1. Method 1 of finding latent heat of fusion of ice using the electrical method. Unless someone has a question. Any question on this method? It is familiar to the one you know in O level, so it should not be a challenge to all of us. Now, the second method is what we know as the method of mixtures. Whereby for the method of mixtures, this is how it's going to be like. In the method of mixtures, we have a stirrer, we have a thermometer, we have a lagging that prevents heat losses, we have water, and then we have to put the ice water mixture. So what happens is warm water at a temperature θ1, a few degrees above the room temperature, is placed in a calorimeter of known mass, mc. This is mass of the calorimeter, mc, and the specific heat capacity, cc. That is, the calorimeter has a mass mc and its specific capacity is cc. Small lumps of dry ice, small cubes of dry ice. Dry ice is, have you ever got ice from a freezer and put it on your tongue? Then it sticks there. That is what we call dry ice. The ice which is non-slippery, which has no liquids on it, which has no liquids melted because of other temperatures. We are using dry ice so that all the ice melting, the melting comes from the heat which has been supplied. So dry ice, dried by absorbent paper, are added into the water. So we have added dry ice into the water at this stage. The mixture is stirred until the temperature is θ2. So you stir the mixture, you know stirring, how you stir with the tea, until the temperature is θ2, below the room temperature. Then the calorimeter is then weighed, and the mass m of ice added is found. If the latent heat, if LF is the specific latent heat of fusion of ice, then heat gained by the calorimeter, which is this one, and heat gained by ice is equal to heat gained by the ice plus heat absorbed by the ice for warming from 0 degrees Celsius to theta 2 degrees Celsius. So we are seeing that saying the heat gained. You know, this diagram which I was trying to show you has a calorimeter. This is the calorimeter inside. Which is lagged. But inside the calorimeter, there was warm water. This water was warm. So the warmed water and the calorimeter were initially at the same temperature. So the heat they had before is the one being lost. So heat lost by, heat lost by this is supposed to be heat lost. Heat lost by the calorimeter and the warm water in cooling, it is not gained, it is lost. You change that in the notes. Heat lost by the warm water and the calorimeter in cooling, because ice is going to cool the water and the calorimeter, is equal to the heat gained by ice in melting, which is latent heat of fusion, then plus heat absorbed by the melted ice. So here we have said heat absorbed by ice from 0 to theta 2 degrees. Because when ice finishes to melt, as we are starting to get a uniform distribution of temperature, the temperature of the melted ice starts increasing from 0 degrees Celsius. So we have that energy because of increase in temperature from 0 to theta 2. Then we have that energy which is required to melt the ice. And by that, mass of the calorimeter, specific heat capacity of the calorimeter, temperature change for the calorimeter from initially the calorimeter was at a temperature T1, so we have gone to a temperature T2. T2 is lower than T1. Plus mass of the water, specific capacity of the warm water, temperature change of the warm water is the same as that of the calorimeter, should give us heat gained by melting ice, mass of the ice, latent heat of fusion of ice, plus mass of melted ice, times specific capacity of the melted ice, times the temperature change of melted ice from theta 2 minus 0. With this equation, you can make latent heat of fusion the subject by saying LF is MCC plus mass of the water, specific capacity of the water, times the temperature change theta 1 minus theta 2 divided by mass of the melted ice times specific capacity of the melted ice times theta 2. There is a mass here. No, this is minus. Mass of the melted ice, specific capacity of the melted ice times theta 2. This is divided by mass of the ice. It's because this one has gone the other side, so it becomes a negative. So that's how this equation came about. Okay, so those are the two methods of investigating latent heat of fusion. One, the electrical method, then two, the method of mixtures. Okay, no questions on this method now. We can talk about the latent heat of vaporization.
Teacher, I have a question.
Go ahead.
Why are you saying is equal to MILF plus MMIC MI theta 2 minus theta 1? Isn't it supposed to be MILF instead? Only
MI what?
mass of ice times latent heat of fusion.
Eh.
Isn't it supposed to be that only? Why are you adding the other one?
Is it? Why am I adding this one? Eh? It is
Yes.
because as we start, look at where we said when you start. Let me go back. There is where I said the mixture is stirred until a temperature theta 2 is reached below the room temperature. Below the room temperature. Now, it means that temperature is beyond 0 degrees. That means all the ice has become melted. Otherwise, if the temperature is not beyond 0 degrees, perhaps some ice can remain there. Now, what happens is all the ice has been melted first using latent heat of fusion. Okay? After all the ice has melted, ice melts at 0. When you look at that graph, we shall see that graph. Ice starts from negative theta, temperature increases up to 0. From 0, all the ice is melting up to point C. At point C, all the ice has turned into water. Now this water will start boiling it until it attains a new temperature, theta 2. But theta 2 is below the room temperature. Okay, so therefore, then the water initially was at a temperature theta 1, which was also at a higher temperature. So it means after all the ice has become water, we continue stirring, and the melted ice plus the water in the calorimeter, they all at the end of the day attain one uniform temperature, which is theta 2. That is why we have also included the heat required to change the temperature of melted ice to temperature theta 2. Have I made sense?
Yes, teacher. Thank you.
Okay. Now we have latent heat of vaporization, whereby latent heat of vaporization is the amount of heat energy required to change the state of a substance from a liquid to vapor, or from vapor to a liquid. And this occurs also at a constant temperature. So according to the definition I've given here, in the notes, you will see that you have latent heat of vaporization is the amount of heat energy required to change the substance from a liquid to vapor state at a constant temperature. Then when we say specific latent heat, if it is specific latent heat, then it is looking at 1 kilogram, whereby it's the amount of heat energy required to change 1 kilogram mass of a substance from a liquid to vapor at a constant temperature. The other one is for the general amount of given mass. This one is for a specific mass, which is 1 kg. So the kinetic theory explanation for this, how it occurs. The kinetic theory explanation is, for evaporation, is that during the change from liquid to vapor state, the heat supplied is used for separating the liquid molecules apart, i.e., increasing the kinetic energy of the molecules. When you are boiling water, at the end of the day, you see vapor coming off from the surface of the water. The reason why this is so, it's because when heating is taking place, the molecules of the liquid, the heat that has been supplied separates those molecules and increases their kinetic energy. When the kinetic energy of the molecules is increased, some of the heat is used to do work to expand the vapor against atmospheric pressure. And in this sense, we can see that as these molecules are freed, those which are more energetic because they have gained kinetic energy, they reach the surface of the liquid and escape in form of vapor. So some of the work is being done to expand the vapor against atmospheric pressure. And now, since kinetic energy of the molecules is not affected or altered, then the temperature will end up remaining constant. But otherwise, if the kinetic energy was changing, then we would also have a change in temperature, since kinetic energy and temperature are directly proportional to each other. You have explanation, questions on that explanation? Then the next is the experiments. So we have the first experiment to determine specific latent heat of vaporization using what we call the method of mixtures. And in this method of mixtures, we generate steam. Of course, steam is generated from here because we want vapor in a flask where a liquid is being heated. Then that vapor comes to this steam trap. When the vapor comes to the steam trap, that vapor can now be subjected to a given liquid. So in the beginning, we say the initial temperature θ1 of the water, and the calorimeter is taken, this water here. The mass of the water, M1 in the calorimeter, is also determined. The liquid in the flask is heated to its boiling point, i.e. θ3. So the boiling point is the temperature. It's not just a point, it's a temperature, yeah, at which the liquid boils. Then steam is passed through the calorimeter. It's passed through the calorimeter with water until let me see if I can. It's here. Steam is passed through the calorimeter with water until there is a measurable temperature change. On its way, the steam passes through the steam trap, which traps any water carried by the steam. The temperature θ2 of the water is in the calorimeter is recorded after stirring. The mass M of the condensed steam is found by weighing. Now the condensed steam is in the form that the steam will condense to water. So that water which comes from steam is what we are calling condensed steam. So the condensed steam is weighed, and thus the mass which has condensed can be predicted. If the mass which has been condensed can be predicted, then we can have the following. Let me take the screenshot.
Teacher,
Yes, please.
is the pipe supposed to touch in the water in the calorimeter or be hung in air?
Because it's going to condense due to the water, it has to touch the water. Was it in hanging? Let me see. Because we are assuming we are going to condense it from the water, from that water. Okay, it has arrived. Okay. So therefore, heat given off by the steam, it is the same as heat given out by the steam plus the heat given out by condensed steam. Because there is steam giving out heat, then there is steam condensing. Yeah? It's all equal to the heat gained by the water and the calorimeter. So that is why this expression looks like this. Heat gained by the steam plus heat gained by the condensed steam. So mass times that rate of fusion, which is mLV, plus mass of condensed steam, which is in form of water, times the temperature change for the condensed steam, is equal to heat absorbed by the water, which is mass of the water, specific capacity of the water, temperature change for the water, plus mass of the calorimeter, specific capacity of the calorimeter, temperature change for the calorimeter. Then you make LV the subject and you get the answer. Then the last experiment here was, or is going to be, the electrical method. The electrical method. The same question you asked me there, the electrical method, the heater should touch the water. Just like in vaporization, in fusion, the heater should touch the ice. When the heater is in the water, it is able to boil the water so that the water can gain steam. Then when you look at this circuit up here, it has a switch. Don't forget to close it. It has a voltmeter across the heater. It has an ammeter and a rheostat. So with that note, we look at the setup as shown. The liquid whose specific heat capacity, whose latent heat of, the liquid whose specific latent heat of vaporization is required is put in a flask. The liquid is heated to its boiling point for some time until the temperature of all parts of the apparatus are steady. So we assume at that instant we have got a uniform distribution of the entire apparatus where we have the flask. At a steady state, all the heat supplied is used in evaporating the liquid and offsetting heat losses. As you can see, it is lagged. The mass M of the liquid from the condenser is collected for a measurable time, T seconds. If the voltmeter and the ammeter readings are V1 and VI1 respectively, then power supplied by the heater is equal to power used in evaporating the liquid plus the heat loss to the surrounding. It is from here that we come up with these equations that I can display here for us to see. So if we come up with these equations, this is how they are going to look like. So the power supplied is I1, V1 is equal to M1 LV plus H to give us equation 1. To eliminate the rate of heat loss, a second experiment is carried out with different power input and evaporation rates. The current I2 and PdV2 and the mass per second are collected in the liquid from the liquid and they are noted. So the second equations will be I2 V2 is equal to M2 LV plus H. When you subtract the two, you can eliminate the heat losses, and you have I2 V2 minus I1 V1 is equal to M2 minus M1 LV. Therefore, latent heat of vaporization can be realized from I2 V2 minus I1 V1 over M2 minus M1. So with that, you would have discussed all the experiments that bring the basis of latent heat. Like I always say, please do not stop just here with what I've given you. Go to the internet and do research and read. Visit the textbooks and read more. See how these explanations, these experiments, we go about them. The next lesson is going to basically be calculations on latent heat. So unless someone has a question for now, the rest of the items that will follow will be calculations on latent heat, and we shall have finished calorimetry. Do you have any questions? So therefore, if no questions, you can call it a day.